Today I am going to discuss the next topic, efficiency of LST related to RBD. You know what is LST and RBD. LST is Latin square design where we have three factors influenced, and RBD, which is nothing but randomized block design, which we have two factors influencing here. Under LST, the three factors which influences the design are nothing but rows, columns and treatments. In RBD, you'll have two factors which are nothing but treatments and blocks. So to compare efficiency means we should compare LST with RBD and you should find out which one is more efficient. So if you observe here, we have three number of factors here and we have two factors here. We cannot directly compare these two and we cannot directly find out the efficiency. First, we are going to apply the uniformity of the trials. Already we have discussed efficiency of RBD or LST. Similar fashion we are going to do uniformity trials we are going to apply. That is, generally if you consider M, I think LST square design, you'll have M number of rows, M number of columns, M number of treatments. I think all are equal here. So you know that under LST, the ANOVA is nothing but source of variation, degrees of freedom, and let us write sum of squares. You have rows, columns, treatments, error and total. Here you have M minus 1, M minus 1, M minus 1, M minus, this is known to you already, M minus 1 into M minus 2 and M square minus 1 and the respective degrees of freedom. This is for LST. If it is for RBD, you know that the same columns, you'll have blocks, treatments, error and total. If there are R, you are going to get R minus 1, S minus 1, R minus 1 into S minus 1, RS minus 1. So if you want to compare or to find out the efficiency of LST over RBD, we define the efficiency as the variance efficiency as sigma 1 square by sigma 2 square, where this is the variance or the mean square error of the second design and this is the of the first design. You know the definition for efficiency. Okay. Now to apply the efficiency of LST or RBD, first of all, you are going to find out you should have here, I said you that three factors and two. First of all, you should balance these two so that one of these should be added to the error. I think you have 1, 2, 3, 4 factors here, 1, 2, 3. So before comparison, there should be equal number of these two. So you are going to, using uniformity trials, you are going to club the treatment with error here so that it becomes three sources of variation here and there. 1, 2, 3. So here also, as if you club treatments with error, you are going to get rows, columns and error. Similarly here source, blocks and treatments. I think these two will be balanced if you club treatments with error degrees of freedom. So before finding the efficiency, using the uniformity of the trials, for LST design, let us say that SE square is the mean square error of the design LST. Let us say that under RBD, SE dash square be the mean square error in RBD. Now using a uniform, let us club these treatments with error degrees of freedom. As a result, the degrees of freedom for error for LST is going to change. That is, you are going to add M minus 1, M minus 2. You are going to add the degrees of freedom of treatments to this error to make the comparison. So this is a regular simplification. If you take out M minus 1 common, M minus 2 plus 1, which is nothing but M minus 1 whole square. So you got degrees of freedom of error in LST is nothing but M minus 1 whole square. Now you got the degrees of freedom is m minus 1 whole square. So error sum of squares. How do you get the error sum of squares? You know that MSE is equal to SSE by its degrees of freedom. If you want this error sum of squares, you should multiply mean square error into degrees of freedom. What is the mean square error of LSD? SE square into m minus 1 whole square. So this is nothing but error sum of squares for under LSD. This is all for LSD. Now you have two cases here where you can consider rows as blocks and the other one is nothing but columns as blocks. Rows as blocks means you have rows, columns, error. You are going to treat that rows as blocks and the other as the treatment. Here you have columns. If you treat as blocks, the rows is going to play the role of treatments. So in the first case, you are going to treat rows as blocks. If you are going to treat rows as blocks, the degrees of freedom for error under RBD is going to change. Up to now we are dealing with, this is up to LSD. Now we are going to conduct the same experiment with RBD. If you want to conduct for the same experimental area RBD, you are going to treat rows as blocks. If you treat rows as blocks, you are going to observe some changes in the degrees of freedom of respect to error. So let us see what is the degrees of freedom. Now error degrees of freedom will be, okay, you are going to, what is the, how much you got the error free, you got the error free degrees of freedom as for the experiment m minus 1 whole square. You are adding the rows also. That row should be added here for the error. So by adding these two, you will get, if m minus 1 is taken out, m minus 1 plus 1, which is nothing but m into m minus 1. This stands for error degrees of freedom under RBD. Got it, girls? Up to here it is LSD. For LSD you have identified by clubbing treatments to the rows, to the error, you got the error degrees of freedom. Now you are going to conduct RBD for the same experimental one by taking rows as blocks. Then for this error degrees of freedom, you are going to add the degrees of freedom of the rows. On the whole, you got error degrees of freedom under RBD as m into m minus 1. I think we need error sum of squares here. Error sum of squares is here, this is nothing but the degrees of freedom of error of LSD. So m minus 1 whole square into SE square plus this is nothing but of rows. Okay, if you are going to club this with, so this is the error sum of squares. How do you get the mean sum of squares? Mean sum of squares is equal to m minus 1 whole square SE square plus m minus 1 into SE square by what is its degrees of freedom. How much you got here? The degrees of freedom here is m into m minus 1. Here you have m minus 1, m minus 1, m minus 1 will be get cancelled. You will get m minus 1 into SE square plus SC square by m. This is nothing but mean sum of squares in RBD by treating rows as blocks. As you are considering rows, columns will be added here. Now what will be the efficiency here? Here efficiency is nothing but sigma, this is nothing but S, you need to consider LSD over RBD means you should write the mean square error of RBD in the numerator and mean square error of LSD in the denominator. This is LSD over RBD. So you'll get RBD if mean square error in the numerator, LSD in the denominator. I hope here let us take under RBD, let SE dash square be the mean sum of squares. So this is nothing but this term represents you SE dash square. So which is nothing but m minus 1 into SE square plus SC square by m divided by SE square. Okay. Now if you simplify this, you'll get a value. You simplify this, you can do this. So MSE square minus SE square plus SE square. MSE square will be get cancelled. You are getting E is a value which is greater than 1. 1 plus a positive quantity which represents E greater than 1. We can conclude that when rows are taken as blocks, you are going to get LST as more RBD is more efficient than LST. As E is more than 1, we can conclude that efficiency E you got more than 1. From there we can conclude that LST is more efficient to RBD. Now let us take columns as blocks. If you are treating columns as blocks, the other factor left over is nothing but rows. Rows degrees of freedom will be added to error degrees of freedom. So here the error similar one, error degrees of freedom is nothing but original degrees of freedom in LST m minus 1 whole square. What is, if columns are treated as blocks, the other factor left over is rows. You are going to add its degrees of freedom here. If you take on m minus 1 whole square common here, the same simplification here also, which is nothing but m into m minus 1. This is the error degrees of freedom when in RBD, when you consider columns as blocks. Now let us find out the error sum of squares in RBD, which is nothing but, I think you need to multiply degrees of freedom with sum of squares using this. Sum of squares into sum of squares, if you want to find out, you should multiply MSE into degrees of freedom. So this is the degrees of freedom. M minus 1 whole square is the degrees of freedom of error, plus this is nothing but of rows. This is the degrees, so you are adding rows, so this will be m minus 1 into SR square. So what is the mean sum of square here? Mean sum of squares, again we will write this as S dash square, which is nothing but error sum of squares by degrees of freedom. So which is nothing but m minus 1 whole square into SE square plus m minus 1 into SR square by what is its degrees of freedom? M into m minus 1. Again, if you want, this is nothing but mean sum of squares. So if you take the same similar step, if you take m minus 1 common, you will get m minus 1 SE square plus m minus 1, no you won't get m minus 1, SR square by m. So this is SE square dash square. Efficiency of, again LST over RBD means you will get efficiency of mean square error of RBD by that of LST. Again the same one, I think if you observe these two, in place of C you got R, everything is same. By the similar one we can say that E is greater than 1 even when we treat columns as blocks. So we can conclude that whenever E, as you got E greater than 1, we can conclude that which one is more efficient? We can conclude that LST is more efficient than RBD. Okay, this is girls. You check this one. I'll send the notes for this also. Check it once. Thank you.